Hello everyone. Welcome to the Crash Course in Energy presented by the Energy Club IIT Bombay. I am Aneri and today's topic is environmental impacts. So let's begin. In this module, we will be learning what exactly is environmental impacts, how to assess them, and we will see the environmental impacts caused by the energy sources, both renewable and non-renewable energy sources. So, what is environmental impact? An environmental impact is defined as any change to the environment. It can be adverse or beneficial, that is, positive or negatively impacting it, and can result from a facility's activities, products, or services. Here, the product we are considering is the energy that is produced. Many examples of environmental impacts include climate change, ocean acidification, acid rain or smog, displacement and extinction of wildlife, and resource depletion like water and land use. Now, let us move on and see how these environmental impacts are assessed or measured. Hello everyone. Methods of assessment. We would think that environmental impact is such a subjective concept, but there are actually ways we can measure them. Let us see how. First is the life cycle assessment. Short form is LCA. Then, energy payback time, EPBT. Third, net energy ratio. And finally, fourth, the greenhouse gas emissions emitted by the energy source. Life cycle assessment. It is known as the cradle to grave method. It is defined as a methodology for assessing environmental impacts associated with all the stages of the life cycle. It can be used for any commercial product, process, or service. And its main objective is to describe and evaluate the overall environmental impacts a certain action can have on the environment. We can see that it is used all the way from the raw material supply to the production to the transportation and energy generation and finally disposal of the waste materials and recycling. The LCA consists of four main steps. First is the goal and scope definition. Here we define what it is that we want to assess, and we also mention who has ordered such an assessment to be taken place. Then, inventory analysis. This mainly is to compile an inventory of relevant energy and material inputs and the associated emissions to the environment. Then is the impact assessment, which is where we evaluate the potential environmental impacts associated with the identified inputs and emissions. And finally, after all of this, is to interpret the results that we have gotten and to make a more informed decision. On this slide, we see an overview of any process. It includes the inputs, which is the raw material and energy needed. Then is the whole process or the life cycle, as I had mentioned in the previous slides. And finally, the outputs, which is a way in which we can use to measure the environmental impacts. They include the atmospheric emissions like greenhouse gases, waterborne wastes, solid wastes, and other releases. Let us see why and why not LCA is a good method for measuring the environmental impacts. First thing is that It presents greenhouse gas emissions for renewable and nuclear energy systems on a scale that allows comparison between the different alternatives. We would think that greenhouse gas emissions are negligible for nuclear energy systems, but since the LCA is for the whole life cycle, it measures the greenhouse gas emissions all the way from building the power plant to transportation of the materials, etc. So there is a considerable amount that needs to be considered. Hence, from that we can compare the different energy sources and make a more informed decision. But there are some reasons why this does have a disadvantage. First is that the long-term potential impacts caused by the increased greenhouse gases in the atmosphere is not really measured by this methodology, and it can be difficult to compare different energy sources due to their long-term impact. Also, there are comparative studies on the land requirements of different electricity generation options. The problem is that the land that is used for the energy production may or may not have alternative uses. Let us see how. On the left side, you see the solar panels placed on the roofs. These roofs do not have any alternative use, so there is not much land use being considered. But on the other hand, we see a hydropower reservoir. This takes up space which can be otherwise used for irrigation, fishing, or recreation. And in that case, LCA does not consider this alternative land use. The second way is energy payback time. This is defined as the time required for the electricity generation equipment to produce the amount of energy equal to the energy used to build, maintain, and fuel this equipment, converted to the corresponding amount of electrical energy. This method is common for comparing different solar PVs. Here we see a representation of the various solar PVs using their energy payback time in years on the y-axis and the materials used or the different types of solar PVs on the x-axis. We can see that the CDTE PV has the fastest energy payback time, which is less than a year. Third way for methods to assess the environmental impact is the net energy ratio. This is defined as the ratio of the net electrical energy produced over a plant's lifetime to the energy required to build, maintain, and fuel the plant over it. There, we have completed methods of assessment. Now, let us go on to see how the various renewable sources of energy affect the environment. Renewable sources. Some examples include solar, wind, geothermal, biofuel, and hydropower. First and foremost is solar energy. Think to yourself, what can be the possible environmental impacts due to solar energy? We have heard that it is renewable, and we have an intuition that there is not much greenhouse gas emissions due to it. Let us see how. Solar power involves two types. First is directly using solar photovoltaics, or otherwise known as solar PV. These photovoltaic cells convert light into electric current using the photovoltaic effect. PV solar energy, the water use is not much, and the life cycle water consumption for such utility scale operations is about 45 liters per megawatt hour for a flat panel PV solar. Only wind power, which consumes essentially no water during operations, has a lower water consumption intensity. However, there is some water needed for cleaning the PV panels. Then we come to the land use, which depends on the scale of the facility. The large-scale solar panels can raise concerns about land use, which causes degradation and habitat loss. It ranges approximately from 3.5 to 10 acres per megawatt. However, such impacts can be minimized by locating these panels on abandoned mining lands, brownfields, or existing transportation corridors. Smaller scale PV arrays, which can be built on homes or on the roofs of buildings, also have minimal land use impact. Some might wonder, unlike wind facilities, there are less opportunities for solar projects to share land with agricultural uses. Why is that? There are a few reasons. One is that the floodplains cannot support solar panels. They will have to be raised as seen in the picture, and hence the cost will increase. Second, due to the solar panels absorbing the sunlight, the temperature rises and changes the weather, interrupting vegetation growth. And third, major solar panels cover large land area. A major area of concern is the hazardous material used to construct these PV cells. The manufacturing process itself includes a number of hazardous materials which are used to clean and purify the semiconductor surface. These chemicals are similar to the ones used in the semiconductor industry, including HCl, sulfuric acid, nitric acid, HF, and 1,1,1-trichloroethane. The amount and type of these chemicals used depends on the type of cell, the amount of cleaning that is needed, and the size of the silicon wafer. There are three types of solar cell materials: thin film, monocrystalline, and polycrystalline. The thin film PV cells contain a number of toxic materials like gallium arsenide, copper indium gallium diacylide, etc., which are toxic and hazardous to the environment. The recycling is expensive, so disposing it off is common. Now let us come to the second type of solar power production, which is by concentrated solar power, CSP, or solar thermal. These use lenses or mirrors and tracking systems to concentrate sunlight. Then they use the resulting heat to generate electricity from conventional steam-driven turbines. We can see an example in the picture shown. Along with the normal PV cell impacts, there are also some additional impacts. First is that it requires a much larger area and hence more land use, which is between 4 and 16.5 acres per megawatt. Second is that CSP systems, like all thermal electrical plants, require water for cooling. Water use depends on the plant design, plant location, and the type of cooling system. There is a dry cooling technology which does not require as much of water. However, the trade-offs to these water savings are higher costs and lower efficiencies, hence not used as frequently. There is also an additional impact of birds getting affected due to the heat concentration of these mirrors and lenses. This diagram represents that water is used for the cooling part of the CSP systems. Coming to the greenhouse gas emissions, the life cycle greenhouse gas emissions for solar power systems are in the range of 22 to 46 grams per kilowatt hour of energy. This differs for both solar PV and solar thermal systems. But to compare, a gas-fired power plant emits around 400 to 600 grams per kilowatt hour of greenhouse gas emissions, which is much, much more. The total life cycle emissions primarily lie in the construction and transportation phase of the materials. A fun fact is BP Solar owns two factories in which the energy used to manufacture solar panels is produced by solar panels, hence giving a net carbon emission equal to zero, which is the goal of many companies in the future.